Good morning everyone. I Aditya from BSC Chemistry on the second year is today here to explain the chapter Diazonium salts for the visually impaired students. Let's start with the introduction. Arena diazonium salts were discovered by the John Peter Gries in 1858. They have the general formula ArN2 plus X minus, where Ar stands from the aryl group and X stands for any anion such as chloride, bromide, nitrate, etc. Aliphatic diazonium salts are also known, but they are highly unstable. They rapidly decompose even at low temperatures, forming the carbocations and nitrogen gas. The reaction is shown here. Therefore, in this unit, we shall discuss about the chemistry and synthetic applications of arena diazonium salts, only particularly with reference to the benzene diazonium chloride nomenclature. Diazonium salts are named by adding the suffix diazonium to the name of compound of the followed by the name of anion. For example, benzene diazonium chloride, para-toluene diazonium hydrogen sulfate, para-chlorobenzene diazonium bromide. Structure of benzene diazonium chloride. Molecular formula. The molecular formula of benzene diazonium chloride is determined from the analytical data and molecular weight determination, that is C6H5N2Cl. Grease structure. Grease purport the structure for the benzene diazonium chloride in which both the nitrogen atoms were directly linked to the benzene nucleus. This structure failed for the following facts. It is the salt-like character. The displacement of both nitrogen atoms by a univalent atom or group in most of its reactions is C6H5N2Cl plus goes to C6H5X. Its reduction to phenylhydrazine, in which only one nitrogen is attached to the benzene ring. Formation of azo compounds by the coupling reactions. Formation of aromatic diazonium salt from the penta substituted anilines. Calculate structure. Calcul proposed the structure for benzene diazonium chloride in which only one nitrogen was linked to the benzene nucleus. Evidence in the favor. This structure explains the most of the drawbacks of Grease structure, such as its reduction to the phenylhydrazine, formation of azo compounds by the coupling reaction, preparation of diazonium salt from penta substituted anilines, and displacement of both the nitrogen atoms by a univalent atom or group. Points against calculus structure. The structure not explain the salt-like character and its instability as compared to azo compounds, since both contain and double bond and linkage. Bloom strand structure. Bloom strand structure for the benzene diazonium chloride in which the nitrogen attached to the benzene ring is pentavalent while the other is trivalent. Evidence in sports. It explains all the objections of structures of calculi and the structure first. Structure 3 is the further supported by the following facts. It is readily soluble in water but not in the common organic solvents. Its complete ionization as shown by the conductimetry measurements. The presence of a triple bond as shown by IR spectroscopy. Its instability as compared to azo compounds, and it also explains the geometrical isomerism as shown by the diazotates or diazoates, which are metallic salt of diazonium hydroxide. Preparation of diazonium salts. Aromatic diazonium salts are prepared by adding a cold aqueous solution of sodium nitrite in the solution or suspension of a primary aromatic amine in an acid at 273 to 278 Kelvin. Diazonium salts are also formed when aromatic primary amines react with the nitrite esters such as amyl nitrite. The nitrite esters needed for the purpose are prepared by the treatment of alcohol with nitrous acid. Thus, the process of conversion of a primary aromatic amine into its diazonium salt is known as diazotization. General procedure for diazotization is the primary aromatic amine is dissolved or suspended in a dilute acid such as hydrochloride or hydrogen sulfate, etc. 3 moles of the acid are generally used for every mole of the amine to be diazotized. 1 mole to form the salt of amine, 1 mole to liberate the nitrous acid from the sodium nitrite, and 1 mole to keep the reaction mixture acidic enough to suppress the undesired side reactions such as coupling of diazonium salts thus formed with free amine. The amine solution and the cold aqueous solution of sodium nitrite is added slowly to it such a rate that the temperature of the reaction mixture does not rise above the 278 Kelvin. The addition of sodium nitrite solution is stopped as soon as the reaction mixture does not rise above 278 Kelvin. The addition of sodium nitrite solution is stopped soon as the reaction mixture does not. For the drops of reaction produced a blue color with starch potassium iodide paper showing the few drops presence of unreacted nitrous acid in the reaction mixture. Too much excess of nitrous acid is generally avoided since it subsequently interferes with the reaction of diazonium salts. The excess of nitrous acid may be destroyed by the addition of urea. Since diazonium salts slowly decompose even at low temperatures, they are used immediately after preparation. Mechanism: the diazotization of amines is believed to occur by the following mechanism. Evidence in support: this mechanism is supported by the observation that aromatic amines containing electron withdrawing groups such as nitrate, nitroxide are less easy to diazotize. This is due to the reason that the nucleophilicity of amino groups is reduced to the electron withdrawing effect of the nitro NO2 groups as shown below. Such amines can, however, be diazotized in acetic acid. Conversely, aromatic amines containing electron donating groups at ortho and para position, example orthotoluidine, para aniside, undergo diazotization then more readily to aniline. Stability of diazonium salts. Aromatic diazonium salts are much more stable than the aliphatic diazonium salts due to the dispersal of positive charge over the benzene ring as shown below. Alternatively, the instability of diazonium salts is due to their tendency to eliminate an exceptionally stable molecule of nitrogen to form the carbocation. Since the phenyl carbocation is much less stable than alkyl carbocation, therefore aromatic diazonium salts have lower tendency to eliminate the nitrogen than aliphatic diazonium salts. In other words, aromatic diazonium salts are more stable than the aliphatic diazonium salts. Physical properties: arene diazonium salts are generally colorless crystalline solids and highly soluble in water. Many diazonium salts, especially nitrites, are dangerously explosive in dry state. Therefore, they are never isolated but are usually prepared in situ and used immediately after the preparation. However, certain diazonium salts such as fluoroborates are relatively insoluble in water and are stable enough to dried and stored. Some diazonium salts can also form complex with the metallic salts such as zinc chloride, example, which are generally insoluble. Chemical properties: arene diazonium salts are highly reactive compounds. Their high reactivity arises due to the excellent living ability of diazo groups such as nitrogen gas. They are extremely useful synthetic reagents in organic chemistry. The reaction of diazonium salts are divided into two categories: reaction in which diazo group is replaced by the monovalent atoms, or reaction in which the nitrogen atoms are retained. Reaction in which the diazo group is replaced by monovalent atoms or group. Some important reactions of this category along with their synthetic applications are discussed below. Replacement by hydrogen deamination. The replacement of the diazo group by the hydrogen or reduction of diazonium salt to arenes is usually brought about by treating a diazonium salt with the hypophosphorus acid at room temperature, preferably in the presence of copper salt as a catalyst. This reaction can be carried out by treating amines with the sodium nitrite and hypophosphoric acid as diazotizing agent. Alternatively, the diazo group may be replaced by hydrogen by heating the arene diazonium salt with the ethanol. The whole process involving the diazotization of an amine followed by the reduction of diazonium salt or a replacement of the diazo group by hydrogen is known as deamination. It may be emphasized here that during the reaction of diazonium salts with ethanol, two products are usually obtained, one involving the replacement of diazo group by hydrogen as discussed above and other the ethoxy group. The relative stability amounts of the two products, however, depends upon the nature of diazo compound and the alcohol used. If a group is absent in the nucleus and ethanol is used, the replacement of diazo group by hydrogen predominate. If on the other hand methanol is used, the predominant product is aryl methyl ether, that is anisole. The synthetic application. The importance of deamination is illustrated by the following application. Synthesis of metabromotoluene. Recall, metabromotoluene cannot be prepared by the direct bromination of toluene or Fiedel-Crafts alkylation in bromobenzene due to the orthoparadirecting nature of methyl group and the bromine atom. Synthesis of 1,3,5 tribromobenzene or same tribromobenzene. Synthesis of 3,5 dibromotoluene. Recall, direct bromination of toluene with bromine in the presence of ferrous bromide gives 2,4 dibromotoluene. Replacement by hydroxyl group. Synthesis, that is synthesis of phenols. Diazonium salts reacts with the water in the presence of acid to form the phenols. The reaction is generally carried out by adding the solution of a diazonium salt to a large volume of the dilute sulfuric acid. Mechanism. This mechanism is carried out by SN1 mechanism as shown below. Synthetic applications. This reaction is especially important since for a few methods are available for the direct introduction of a hydroxyl group into the benzene nucleus. That is synthesis of metanitrophenol. Third one is the replacement by halogens. Different methods are used depending upon the halogen to be introduced. Firstly, replacement by the chlorine or bromine, that is Sandemeyer reaction. Aryl chlorides and bromides can easily be prepared by treating a freshly prepared cold aqueous solution of an arene diazonium salt with a solution of cuprous chloride in hydrochloric acid or cuprous bromide in hydrobromic acid. This reaction is called Sandemeyer reaction and gives a aryl halides in 60 to 80% yield. It may be noted here that it is the halogen which is attached to the copper which enters the nucleus. Mechanism of Sandemeyer reaction is believed to be occur by the free radical pathway as delineated below. Gattermann reaction. It is a modification of Sandemeyer reaction in which a copper powder and a hydrogen halide are used instead of cuprous halide dissolved in the corresponding hydrogen halide. Yields are often lower, around 40% than those obtained by the Sandemeyer reaction. Synthetic application. The synthesis of the 1,2,3 tribromobenzene. Replacement by iodine. The replacement of the diazo group by iodine does not require cuprous iodide or copper as a catalyst. It is simply achieved by treating a diazonium salt with a potassium iodide or a solution of iodine in potassium iodide. That is synthesis of para-iodonitrobenzene. Replacement by fluorine, that is Bald-Schiemann reaction. When aqueous solution of diazonium salt is treated with fluoroboric acid, that is HBF4, diazonium fluoroburate get precipitated. It is filtered and dried. Unlike other diazonium salts, diazonium fluorobates are fairly stable compounds. When diazonium fluorobates is heated, it decomposes to produce aryl fluoride and boron trifluoride. Mechanism is occurred by the SN1 mechanism. Synthetic application, synthesis of fluorobenzene. Replacement by the cyano-CN group, that is the synthesis of nitriles. Aryl nitriles can be prepared by treating a diazonium salt with a cuprous cyanide or potassium cyanide and a copper powder. To avoid the loss of cyanide such as hydrocyanide, the diazonium salt solution is first neutralized with sodium carbonate and then treated with the cuprous cyanide. This reaction is known as modified Sandemeyer reaction. Synthetic applications. Since hydrolysis of nitriles give carboxylic acids, therefore the synthesis of the nitriles provides with an excellent method for the preparation of carboxylic acid from the nitro compounds. For example, replacement by the nitro group. Nitro compounds are generally prepared by treating an arena diazonium fluoroburate with an aqueous solution of sodium nitrite in presence of a copper powder. Replacement by a arsenic acid, that is Bart reaction. Treatment of an arene diazonium salt with the sodium arsenic in presence of copper sulfate followed by the acidification of gives an aryl sonic acid. For example, replacement by an aryl group, that is Gomberg-Bachmann reaction. When an arene diazonium salt is treated with an aromatic compound in presence of an aqueous alkali, biaryls are formed. Yields are usually less than 40%. Mechanism. The reaction is believed to be occur by the free radical mechanism. In alkaline medium, the diazonium salt are converted to the corresponding azo compounds which decomposes to form the aryl radicals. B. Reaction in which nitrogen is retained. Reduction to aryl hydrazines. Arene diazonium salts upon reduction give good yields of aryl hydrazines. This reduction can be brought about by a number of reagents such as stannous chloride and hydrochloride, sodium sulfite, sodium hydrosulfite, and even electrically. If, however, strong reducing agent such as zinc in the presence of hydrochloride is used, the product is an aromatic amine. Mechanism of reduction of diazonium salts with sodium sulfite. The reaction probably occurs through the nucleophilic attack by the sulfur atom of the sulfite ion on both the nitrogen atoms, forming the dianion of hydrazine sulfonic acid, which is then converted into hydrazine in presence of acid. Coupling reactions. Arene diazonium salts react with highly reactive aromatic compounds such as phenols and amines to form the brightly colored azo compounds. This reaction is known as coupling reaction and is extensively used in the azo dye industry. Whereas coupling with the phenols can occur in basic medium, that of amines occurs in faintly acidic medium at 273 to 278 Kelvin. Coupling usually occurred as the para position with respect to the OH or the NH2 group. However, if the para position is blocked, it occurs at the ortho position. If a compound contains both an amino group as well as a hydroxyl group at para position with respect to each other, then the orientation of the coupling reaction can be changed by changing the pH of medium. The well indicator methyl orange is widely used in the acid-base titrations is obtained coupling the diazonium salts of sulfanilic acid with N, and dimethylaniline. Mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride and phenols or amines is an example of electrophilic substitution reaction in which diazonium ion act as the electrophile while phenol or amine act as a nucleophile. Coupling with phenols. Since benzene diazonium ions are only weak electrophiles, therefore strong nucleophiles are added for the reaction to occur. Further, since phenol is weakly nucleophilic but phenoxide ion is strongly nucleophilic, therefore coupling reactions of the phenol usually carried out in the alkaline medium. Role of pH. The pH of the medium plays an important role in the coupling of phenols. As stated above, the coupling of phenols is carried out in a weakly basic medium as explained above. In the alkaline medium, the diazonium salt first forms diazonium hydroxide, which immediately rearranges to form the diazo hydroxide, which further reacts with the alkali to form the corresponding salt called the diazotate. All these three species in fact exist in equilibrium as shown below. Since at high concentration of hydroxide ions, the equilibrium will shift in the favor of diazo hydroxide and diazotate, and both of which do not couple. Therefore, for the desired coupling reaction to occur, the pH must be kept as low as possible. In the alkaline medium, however, a too low pH would suppress the dissociation of phenol to the phenoxide ion. Therefore, to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for the coupling reaction is between 9 to 10. Coupling with amine, that is tertiary amine. The mechanism of the coupling reaction of the diazonium salts with tertiary amine similar to that of phenols, except that is coupling reaction under the weakly acidic conditions. Reaction with the primary and secondary amines. Coupling of the diazonium salts with the primary or secondary amines occurs in neutral or mildly alkaline medium. Here, NH2 group of the amine first attack the diazonium cation to form the diazoaminobenzene. However, when the diazoaminobenzene thus formed is heated in the presence of acidic medium, it undergoes the diazoamino-azo rearrangement to form the para-aminobenzene by the following mechanism. Role of pH. In the presence of high concentration of H positive ion, a lone pair of electrons on the nitrogen atom accept the protons. As a result, the amine exists predominantly in the protonated form as shown below. Due to the absence of the lone pair of the electrons of the nitrogen atom, the amine is no longer nucleophile, and hence the coupling reaction will not occur at high concentration of H positive ions, that is low pH. Further, as explained above, Too high alkalinity, that is high pH, will also not favor the coupling reaction by forming the unreactive diazohydroxide or diazotate in significant account. Therefore, an optimum pH of 4 to 5 is employed for